Welcome to the design example for lecture 6.8 on PID controller design. So we're going to go through a design example in MATLAB, just a pretty straightforward PID controller design using the method, the procedure that is outlined in lecture 6.8, and I give us some requirements to meet in that, so we'll do our best to do so. So let a system have plant transfer function given in 650 here. So we've got a 0 and 2 poles. Design a PID controller with a unity feedback such that the closed loop rise time is about 5/100ths of a second. The overshoot is less than 5%, and the steady state error is 0 for a step command. So less than 5% and 0 for a step command. So those are the three requirements we have. One of them is for a certain steady state error, and the other two are transient response requirements. So the first thing that we'll do is discuss what our procedure here is, or what our approach is going to be. We'll use MATLAB to do the actual analysis for us. And of course, our first step is to decide if a PID controller is the right controller for this problem. The PID controller is going to have an integrator in there, and that integrator is there primarily to improve the steady state response in the sense that we want a small steady state error, or 0 in this case, steady state error, for a step command. Since our plant has no integrators in it, it is type 0, okay? So integral compensation is required to yield 0 steady state error for a step command. Okay, that's something that we learned back in the chapter on steady state error. And the integrator can be introduced using integral compensation. So a PI, the I part of it, D controller. So the integral compensator is required to meet this step command steady state error requirement. So PID is looking good. P and D are going to be used primarily to meet the transient response requirements. And of course, we always have an implied assumption that we should have a stable system here too. So our stability requirements are not explicit in this problem, but we'll of course want a stable system that is created when we include the controller. So next, we must determine what the specified transient response criteria imply for the locations of our closed loop poles. Let one of these desired pole locations be called psi, okay? And this section is called determining psi, which is the main thing we're doing here. The transient response performance criteria are as follows. So this is just creating MATLAB objects that represent these. So the rise time is 5/100ths of a second. And the overshoot in percentage is 5%, which is the maximum overshoot that we're looking for. The second order approximation from chapter 3 tells us via figure 3.3 that the rise time specification implies a specific ratio between natural frequency and the implicit function f of zeta defined in figure 3.3. So if we look at the textbook, we have here the figure 3.3 in chapter 3. And we have a relationship here between the rise time multiplied by the natural frequency and the damping ratio zeta. So we're going to use that relationship to help us specify where in the S-plane we would like our dominant closed loop poles to be in order to meet our transient response requirements. So We know that the rise time should be around 0.05. So we'll set TR to be 0.05, and we'll use this figure to relate the natural frequency. Once again, it's the second order approximation. So once we include our compensators, we won't have a second order system responding, so it'll just be an approximation. It was always an approximation because we even had a 0 in the plant transfer function. So the natural frequency and damping ratio via the second order approximation are related in this figure. So we'll use this in a moment. But we don't have the natural frequency or the damping ratio at this point, so we just have this relationship that we aren't using quite yet. Now, the minimum angle is determined from the overshoot specification via the relations given in these two equations. So the angle of the design point, so the picture we're imagining here is that we've got the S-plane and we've got a specific design point, psi, okay? And that design point you could think of it as being represented by an imaginary plus a real number or a complex number, where this is the real axis and this is the imaginary axis. And that is, of course, equivalent to a magnitude of psi and a phase of psi, okay? So we need to know the magnitude and phase of psi to know where we'd like to be, or we'd like our closed loop poles to be, the dominant ones at least. And we also would like to know of course, the real and imaginary parts, which are given as the real axis coordinate and then the imaginary axis coordinate for this psi. So since we're given the percent overshoot, the percent overshoot actually specifies via equation 653 what the damping ratio should be, assuming a second order approximation, which is again from chapter 3. So this relationship here allows us to take our required percent overshoot, or our target percent overshoot, you could say, and calculate what zeta that corresponds to. And that zeta is related to what the angle of psi is here. So we'll use those two equations to find that angle of psi. If you use MATLAB, so we're going to be using MATLAB in a Jupyter environment here, which is a little bit non-standard, but actually totally doable. So I will specify this rise time and this overshoot, like we said above, and then we can compute what zeta, the damping ratio, and the psi angle should be to correspond to that percent overshoot. So zeta is 0.6901. Now we're able to use that result here. So this we used to find psi, the angle of psi. So that is specified. So that's good. So we've got the angle, and now we need to know the magnitude of psi. We can find the magnitude of psi by the fact that it's related to the natural frequency via a direct equality. So we know that if we can find the natural frequency, we can also find the magnitude of psi, and our design point is fully specified. So the natural frequency zeta rise time relationship given in figure 3.3 says, now that we have our zeta, we go to 0.69, which is right here, and we follow it up to the curve, and that corresponds to about 2.1. So the rise time times omega n equals 2.1. We know the rise time was specified to be 0.05, so we can solve for the natural frequency to be 2.1 divided by the rise time. which is also equal to the natural frequency omega n. So we said psi magnitude because that's what we're interested in. The natural frequency is equal to that psi magnitude. So 42 is what it came out to be. So now we've got the angle given. We already computed that in the previous step. And now we have the magnitude given. And therefore, we've fully specified what our design point is, what the location of our desired second order approximation closed loop poles should be, dominant closed loop poles should be. So we can convert that into a rectangularly represented number. So the real part, just a simple trigonometric relationship between the magnitude and phase and the real and imaginary parts. So the usual relationships are computed there. And we find that our psi location that we're going to attempt to get our system in the enclosed loop to behave like, if it was to behave perfectly like a second order system with no zeros, this is exactly where we would like that design point to be, where we'd like that closed loop pole to show up. So this is going to be our goal, and we know it's an approximation, but it's at least a place to start, a place to sort of bootstrap from. So this is the design target for the dominant closed loop poles. As usual, it depends on the second order approximation, so we will need to simulate to determine the actual performance, as virtually always we need to do. So, great. So that's, go ahead and compute these, and we're caught up. Now, proportional control. We design a proportional controller that gets us as close as possible to psi, our design point. The root locus is shown in figure 6.15. So if we just do our locus, so over here, if we just do our locus, and we'll also put our design point on here. So if we put text, we put in for the x value the real part of psi, and for the y value the imaginary part of psi, we can plot this root locus and see that it does not go through our design point. Okay, which means that we're going to need derivative compensation. If you're going to, at least using the methods that we're using, if you're going to move the root locus itself, the way to do that is to use a derivative compensator or a lead compensator if you so choose. So we're going to need to move this root locus. But we can use a proportional controller to get as close as we can to this point. So if you use the data cursor in MATLAB and you click there, you can see that given these different gain values, you can get somewhere near the design point, and that'll be our proportional control design. So we'll just use that. I used k of 64. This is wrong. There's a k of 64. So I tried a gain of 64, which if you look at this again, a gain of 64 puts us out about here. And of course it's not on the design point, but it's better than nothing. So the proportional controller can get us close. So we'll use a gain of 64. And we'll even create a closed loop transfer function. So this is a closed loop transfer function with just a proportional controller in there. Okay, so we create that. Now we'll do some derivative compensation. So we try cascade derivative compensation with this compensator. This is always our derivative compensation compensator. We put a 0 at some location ZC, and that is the 0 compensator. So for now, we set K2 equal to 1, and from equation 621, we compute the compensator zero angle contribution. So this is the amount of angle that we need to contribute so that the angle criterion of the root locus is met at the design point. So we have used this before when we did our PID controller design. And it's nice because you can actually calculate this using a simple formula, pi minus the angle of the transfer function evaluated at psi, okay? So that's the amount we need to contribute. And it turns out to be 13.1 degrees we need to contribute with this 0. So in order to figure out where to put that z, that 0 for the zero compensator, we actually can back out using equation 6.57, which is essentially just a trigonometric relationship, what the zero location should be. We compute it here in MATLAB. So computed 13.1 degrees for theta c, and then negative 159 is the zero compensator, zero location. So negative 159 is what comes out. Let's construct the compensator sans tuned gain K2, without it, and construct the corresponding root locus. So if we construct the compensator without a gain, if we use ZPK, we can specify the zero location, if there are any poles, which there are not, and then the overall gain, which we're going to set to 1 to start. Okay, we're going to do a root locus here, and we see by construction we have placed the design point on the root locus. Okay, that has to be the case. That has to happen every time. And as long as we've done our calculations correctly, it should be on the root locus. Great. That means that we can adjust the gain now. And we see that zero compensator showing up way out here. It moved things around in the root locus so that we were able to go through that design point. Great. Derivative compensation is working great. Now we could adjust our gain and try to get right on the design point, which looks like it's going to be about 0.005 for the gain. And if you because we know that this design point occurs on the root locus, you can actually use the relationship given in equation 658 to figure out what that gain should be. So we can actually, if you know that your point is on the root locus, you want to find out what gain that corresponds to, you can use this formula to find it. It's a really nice formula. It means we don't actually have to use the data cursor, and we can compute what the gain should be to be right on that point. If you do so, you find out, just like what the data cursor appeared to show, the gain should be about 0.0053. Okay, so there's our K2. And we see that we're right on the design point with our root locus. So our placement of psi depended on the second order approximation's accuracy, which in this case is questionable due to the proximity of a third closed loop pole. In any case, we simulate the response to the test efficacy of the PD controller design and to compare it with the PD controller. So we go ahead and do the simulation, which is computer K2. We can create a time array using linspace. We'll do a step response simulation using the proportional closed loop controller transfer function, and a closed loop transfer function using the PD controller. And we'll compute both to compare them to see how the proportional relates to the PD control response, and we get this graph for the two responses together. I'll actually show us in here because it's a little bit easier to see. So the P controller is in blue, and it has a pretty quick rise time, actually. The rise time was actually quicker than what we're looking for, which is about 0.05. And we've got a percent overshoot here for the proportional controller that's definitely too large. It's over 10% for sure. And once again, we see that we've got a steady state error here, right? This is a steady state error, and we're going to want to take care of that with an integral compensator. It should be at 1 as time approaches infinity. It is, in fact, at about 0.9 something, which is not ideal. So we can use the step info function to compute specifically from the simulated step responses what the rise time is and what the percent overshoot is. We see that the rise time is pretty good. It's a little low. We want it to be about 0.05, and the percent overshoot is certainly too much. We want it to be less than 5%. So our second order approximation that led to this design is not very accurate because we missed the percent overshoot and we missed the rise time. Not terrible though. We're in the ballpark, right? Which is all we can hope for with the second order approximation. Before we start tuning this design, let's fix the steady state error by including an integral compensator. So we could tune it at this point, but we're gonna screw it up a little bit when we include the integral compensator. So let's use that integral compensation, see what happens. Maybe things will get better. You never really know before you start how each compensator is going to affect everything. The complexity has increased to the point where we're not totally sure. If we include the integral compensator, will the overshoot get better? Will it get worse? So let's go ahead and see what happens. The integral compensator has its usual form, a 0 at zi and a pole at the origin, otherwise known as an integrator. We're less concerned with about affecting our transient response with this compensator because we need some help doing so in any case. So, especially if it affects it positively, that's good. So we aren't going to be super aggressive with an integral compensator that doesn't affect the transient response. Remember, the closer you make that 0, this zi, to the origin, the smaller the impact will be on the root locus. So the transient response won't be affected. But in this case, we're open to that transient response being affected. So we'll see. Be a little bit more lax about our not affecting the transient response rule on this. So we specify it, and then we construct the transfer function without any gain associated with it. We'll just throw in the 0 and then the pole at the origin at 0 and then 1 for the gain. Now a root locus wouldn't be particularly helpful since second order approximation is poor in this case and getting worse by the minute. Instead, we proceed directly to simulation. So we'll do feedback. We'll use the compensator from before. We'll also include the compensator for the integrator, and we'll use the feedback function to create the closed loop transfer function, and then we'll find the step response using step. Okay, so we'll plot again these step responses, and we'll look at the step info. So let's look at the responses first. We've got the P in blue, the PD in red, and then the PID in yellow. We see that, of course, the integrator actually helped us with our steady state error, which is good. This is what we were expecting to see when we included the integral compensation. We expect 0 steady state error as time goes to infinity because we have a type 1 system once we've included the integrator, and a step command. So in that case, if you go back to that analysis of steady state error, you'll see that a type 1 system for a step input or a step command is going to give us 0 steady state error as time goes to infinity. So we've got the PID controller that's looking pretty good overall. It's definitely looking better than the proportional or the proportional derivative controllers. And if we look at the rise time and the percent overshoot performance, so our transient response performance, our rise time is still a little low. Okay, we'd like that to be up closer to about 0.05. And the percent overshoot is still high. We'd like it to be below 5%. So we're going to try to tweak. So we've got a PID controller. It's performing pretty well. At this point, we don't know how each of our gains or 0 locations are going to affect things too much. I mean, we have some ideas, but there are a bunch of knobs that we have. We have the 3 gains, and we also have the 2 0 locations. So we can kind of mess with these a little bit. So what we do is we mess with K3 gain. We mess with the derivative compensator 0 location. We mess with the integral compensator 0 location. And we recompute the compensators, and then we combine them all into a closed loop transfer function again. And this closed loop transfer function will give the step response if we use the step input for simulation. So we'll again do our simulation and plotting. And we get this tweaked PID, the purple trace here, which has the same steady state error improvement as the original PID controller. But we've managed to really knock down this overshoot. Okay, this overshoot's quite a bit lower than it was. Our rise time is also better. It's close to 0.05%. Overshoot is less than 5%. It's actually quite a bit less than 5%. So we've been pretty aggressive with this tweaking, and we were able to meet both specifications, even though we had to kind of massively tweak our controllers to make that happen. It was challenging because whenever you increase the rise time, the overshoot also increases. So we actually had to move around the zeros a little bit to make it all work for us. All things considered, though, we were able to make the design requirements work, and we were even able to make them work quite well. So percent overshoot is actually much lower than 5%, the 5% that was required. So not a bad job on this design overall. We should compute the PID gains, okay? So we've got our controller, our closed loop controller, that's given here, K1 times K2 times K3 times CI sans times CD sans. So those are the integral compensator and the derivative compensator without their gains, okay? Their gains are K2 and K3. So let's use the equations that are given in this lecture, in lecture 6.8, to compute what Ki, Kd, and Kp are. So if you scroll way up, back here, we can compute them from these equations, 647 through 49. So let's do that in MATLAB. We've got Kp equals negative K1 times K2 times K3. So negative K1 times K2 times K3 times Zd plus Zi. I think I called them Zd. plus Z I put underscores ZD plus ZI. And we've got KI equals K1 times K2 times K3 times ZI times ZD. So we can just sort of cheat here a little bit and reuse a lot of the previous one. And then we've got KD equals K1 times K2 times K3. Great. So we go ahead and compute them. We get KP being about 45, KI being about 272, and KD being about 1.4. So that is how to go through the design process for a PID controller, and to go back and figure out what the proportional gain is, the integral gain, and the derivative gain are. So thanks for watching the example, and I'll see you next time.